Therefore, we conclude that the experimental features of the photoelectric effect are: for a given photosensitive material and frequency is greater than the threshold frequency, nu is greater than nu naught, the photoelectric current I is directly proportional to the intensity. That means if intensity increases, photocurrent also increases. Second point is, for a given photosensitive material, there exists a threshold frequency nu naught, which is the minimum cutoff frequency of the incident radiation below which no emission of the photoelectron take place, no matter how intense the incident radiation is. That means if frequency is less than nu naught, nu is greater than less than nu naught, then there will be no emission whatever the intensity of the radiation is. Third point is, stopping potential V naught is independent of the intensity of the incident radiation. For nu greater than nu naught, stopping potential V naught, which is equivalently kinetic energy maximum of the emitted photoelectrons, because K max will be equal to E into V naught, where V naught is the stopping potential. So, stopping potential increases with the frequency of the incident radiation, but it is independent of the intensity. If we use the Einstein equation, it is EV naught, this is the stopping energy applied, because E is the charge on the electron and V naught is the stopping potential, and this will be equal to the kinetic energy which is maximum for the electron, and it is a difference of the energy of incident radiation and the work function. Fifth point is, photoelectric emission is an instantaneous process without any apparent time lag, because it takes a time of order of 10 to the power minus 9 seconds or less, even when the intensity of the incident radiation is too low. That means emission take place instantaneously, independent of the intensity of the radiation. Let's do some problem. Question is, when a photosensitive material is irradiated with light of frequency nu, the maximum speed of the emitted photoelectron equals Vmax. The graph shown in the figure gives a plot of Vmax square varying with frequency nu. Obtain the expression for Planck's constant, work function of given photosensitive material in terms of the parameter Ln and the mass m of the electron, and how is threshold frequency determined from the plot. If we see the plot, this is a graph between the Vmax square and frequency. From the Einstein photoelectric equation, we know K max is equal to h nu minus h nu naught. This h nu is the energy of incident photon and h nu naught is the work function of the material surface. This K max can be written as half m is the mass of electron and V max square, that is equal to h nu minus h nu naught. So V max square is equal to 2h by m into nu minus 2h by m into nu naught. And this is the graph. Compare with the equation of a straight line, it is y equal to mx plus c. Therefore, slope of the graph is 2h by m. Here this m refers slope and here this m refers mass of electron. So these two are different. And intercept c is minus 2h by m. So comparing this from the graph, here the graph is having the angle say theta with the frequency axis, then this angle theta is also here. So slope is equal to tan theta and tan theta will be equal to perpendicular by base, that is L by n. So using the first, the slope is L by n and it is equal to 2h by m. Therefore, Planck's constant h will be equal to m into L by 2n. Second is, from the equation of Vmax square versus frequency, which is a straight line, the value of 2h by m into nu naught is equal to the c, and c is the intercept made by the line on the y-axis, which is represented here by L. Therefore, h nu naught, this is the work function of the material, and it will be equal to m into L by 2. So this is the work function. Third is, how is threshold frequency determined from the plot? Here, the graph cutting the frequency axis at a point, and this point refers the frequency which is the threshold frequency, because for the frequency greater than this threshold frequency, emission of the photoelectron take place, and below this frequency there will be no emission. So we can say graph cutting frequency axis refer threshold frequency nu naught. Next question is, monochromatic light of the frequency 6.0 into 10 power 14 Hz is produced by a laser. The power emitted is 2.0 into 10 power minus 3 watt. What is the energy of the photon in the light beam? The monochromatic light means it has a single color or the wavelength. The energy of the photon is E equal to h nu. Here h is the Planck's constant having the value 6.6 into 10 power minus 34 joule second, and the frequency of the radiation is 6 into 10 power 14 Hz. Therefore, it will give 39.6 into 10 raised to power minus 20 joule, or we can say it is 3.96 into 10 raised to power minus 90 joule. This is the energy of the photon. In second part, how many photons per second on an average emitted by the source? The power emitted P is given 2.0 into 10 power minus 3 watt, or we can say it is 2.0 into 10 power minus 3 joule per second. That means 2.0 into 10 power minus 3 joule energy is released in 1 second. And if we divide this much joule by the energy of the single photon, that is the 3.96 into 10 raised to the power minus 19 in 1 second, that means this much number of the photons, this is the total energy, this is the energy of the single photon. So total energy divided by the energy of the single photon, this will give the total number of photons emitted in 1 second. Therefore, on solving, it is approximately 5 into 10 raised to power 15 photons per second are emitted from the source. Next question is, the work function of a cesium is 2.14 electron volt. Find the threshold frequency of the cesium. We know work function phi naught is equal to h nu naught. And we have to find the threshold frequency. So threshold frequency will be equal to the work function divided by the Planck's constant. And work function is given by 2.14 electron volt, and Planck's constant is 6.6 into 10 power minus 34 joule second. We have to convert this electron volt into the joule. So it is 2.14 multiplied by 1.6 into 10 raised to the power minus 19. So this gives the work function is joule divided by 6.6 into 10 power minus 34, 3.924 divided by 6.6 into 10 raised to the power 15, and it is approximately equal to 5.1 into 10 power 14 Hertz. Second part is the wavelength of the incident light if the photocurrent is brought to 0 by a stopping potential of the 0.60 volt. For this we use the Einstein photoelectric equation, As per the Einstein photoelectric equation, h nu is equal to, that is the energy of photon, incident photon, equal to the work function plus the maximum kinetic energy of the emitted photoelectron. And this maximum kinetic energy of the emitted photoelectron will be equal to EV naught. This is the product of the charge of electron and the stopping potential. We are given that the work function is 2.14 electron volt and the stopping potential is 0.6 volt. Therefore, the maximum kinetic energy will be 0.60 volt multiplied by E, that is the 0.60 electron volt. So, total energy of the incident photon is 2.74 electron volt. Now, we have to find the wavelength of the incident radiation. So, h nu is hc by lambda, that is equal to 2.74 electron volt, and we know that hc is 1240 electron volt nanometer. This is a very important relation to solve such problems in a few steps. Therefore, lambda will be equal to hc by 2.74 electron volt, and here hc is 1240 electron volt nanometer divided by 2.74 electron volt. So we will get the wavelength as 1240 by 2.74 nanometer, and it will be equal to